in NumPy and SciPy. Our speaker has written an O'Reilly book on the subject, and he's a data scientist at Stitch Fix. Please join me in welcoming Ellie Bressert.
So, hi everyone. Can you hear me with the microphone? Okay. So thank you very much for having me here today. I have given talks at Python clubs before, but this is by far the most impressive size. So it's very exciting to be here to talk about NumPy and SciPy. So before we go on, I just really kind of want to give a little bit of a quick background why NumPy and SciPy are really important for Python. And before that as well, I'd also like to state that we're not only going to cover NumPy and SciPy, which was originally covered in the book, but go a little bit further. There's been some real development in the numerical analysis data sphere, essentially, that should be added to that book, and hopefully will in the future at some point. So, NumPy and SciPy both have a history in the sense of enabling Python for numerical analysis. When Python first came out, it was a beautiful language. It had great syntax. It had very high readability. And because of that, it's been used in many different projects. NASA, for example, loves to use it because one programmer can use it, and these would be like mission-critical type projects where things are really depending on it. You don't want, let's say, some type of satellite to fall apart because they miscalculated something when someone was reprogramming it from someone else. The downside of Python originally was that the data structures, or the ways that it could store data internally in the Python environment, wasn't necessarily efficient for numerical data. So like a list, for example, would allow you to essentially store data, almost any type of data that you want within a list. And you could store an object, store a string, store another list, store a dictionary, and so forth. But that makes it very cumbersome to basically go through that type of data or that type of structure and do numerical analysis. So Travis Oliphant and many of the open source community people had put together things like what were originally called Numerical Python and is now known as NumPy and SciPy. So numerical arrays I'll cover in a little bit, and we'll also cover a little bit of what SciPy means on top of that, and then about some of the more recent development that's really added a lot to the data analysis sphere. Before I go on, I'd like to kind of get an idea of the, let's say, the audience. How many people here actually use NumPy and SciPy? Okay, so about a little bit over half of the room. Anyone familiar with pandas? Okay, a little bit less, but so we're going to cover those. So for those people who do know NumPy and SciPy and pandas, this will be maybe a little bit of repetition, but I'll be talking about some of the things that you should be using an extension to it. So things that may help you with the analysis. So when people talk about questions of like, what's the best way to do statistics and probability type studies on something, so something that could be used as a tool for scientific analysis, the most common answer in saying what's the most important thing that you can do is exploratory data analysis. So there's some real fundamental books that are based on this topic itself. And the reason is that when you're looking at data, actually, let's go about it in this way instead. When you're getting ready to do some analysis on data, and you have no idea what the data looks like, it's essentially trying to drive a car blindfolded. It's not a great way to actually start doing analysis on that data. You really want to kind of get an intuitional understanding of what the data is doing, see what the type of distributions are present, what kind of extreme cases are there. For example, let's say you have some data about how to buy a car or to sell a car for an optimal price. There could be some outliers in there. There could be someone who put a car and has overpriced it by maybe even, let's say, 2 sigma or 3 sigma above the average. And that's not necessarily something that would represent the mean itself. So seeing those types of outliers is very important, and in some cases it's important to clip them, as well as maybe it's important to know them and still continue using that in your analysis. So exploratory data analysis does help you understand what's happening with that data and help you decide how you're going to move forward with the analysis. In the case of my background, which was originally astrophysics before I went into data science, we have many outliers. And the reason is that in terms of space, stars are logarithmic in brightness. So, and this is the way we also see visually in terms of brightness. So the scaling of flux for a point source somewhere in the sky is going to be either extremely dim or extremely high. And in many cases, you have to understand that in the sense of outliers as well. So you may have something called supernova, when a star explodes, become extremely bright, much brighter than almost any star in the sky. And identifying those types of outliers is very important when you're also doing your data analysis. So trying to understand the stellar population can be very, very complicated. But as long as you understand the extremes, the distribution, the mean, the median, it really does help you prepare for the way that you're going to do it. So I can't enunciate enough. Before you do data analysis, make sure that you really explore it and understand it. The best way to do it, in the sense of data itself, is to visualize it. So fortunately, Python, I'd say probably in the last, maybe the last 8 years, starting about 10 years ago, there were some packages that were trying to plot data, but they were quite painful. I've forgotten the names of the packages back then, but they didn't really do much in terms of enabling us to do very, let's say, like dynamic or interesting plotting capabilities. It's just time that you typically see in a LaTeX paper for academia, but it was just very static, and you didn't have a lot of flexibility in the way that you could do things. But there was one package that took everything by storm, and that was a package called Matplotlib. It used a syntax or an API format that was similar to Matplotlib. Matplotlib using a syntax that was similar to MATLAB. So for those of you that are familiar with MATLAB and haven't played with Matplotlib, you'd feel right at home using Matplotlib. But that was starting about maybe 2006 is when I think Matplotlib was really starting to lift off, and it's been doing exceedingly well since then. But there's been, I'd say, some rather new development recently in the last few years, which is that the browser has become, the internet browser, has become the real backend for displaying information. We all know about D3.js, the JavaScript package that basically allows us to interact with data and can basically display that information in nearly any way that we can dream of. Unfortunately, a package like Matplotlib wouldn't allow us to work with it in that same fashion. So there's been a lot of work recently, and if anyone went to PyData at Facebook, who was at PyData recently? Okay. So you may have, if you went there, you would probably remember that one of the highlights of the discussions there, or the presentation, was about data visualization and what packages are needed, or what features are needed in the packages that we have today. And everyone pretty much agreed that the browser is the best way to do it. So there have been ways to try and push forward with that, and one of them is called NPLD3. It's written by a very bright fellow up in Seattle. His name is Jake Vanderfass. Some of you may know his blog. He's written NPLD3 basically to take Matplotlib and, without you really having to do any worry, convert that straight into D3. So if you use the IPython notebook, or you get loaded straight into the IPython notebook, a plot that was static has now become dynamic. You can interact with it. So this is, I would say, a big move forward for debugging capabilities. There's two others that I'd like to mention. One is Plotly, which is also an interesting package. It's basically a universal package almost in a sense for plotting, because it can be connected from many different types of languages. So not only is it available in R or in Python, but others as well. So it's becoming, I'd say, a rather big force in terms of the plotting sphere. And then last but not least is Bokeh. Bokeh is another package that's being developed by the Continuum Analytics group. So these people are kind of the powerhouses in terms of what's happening in scientific analysis, as well as Enthos as well. And moving a little bit out of the browser, this is going again to enunciate the fact that you should explore your data in some type of visual form, is Glue. So this is a package that isn't too well known, unfortunately, but it's developed by someone from Harvard who comes from astrophysics, so that's the reason why I know about this package. But it allows you to explore data in a highly interactive and connective way. So you can basically highlight information in one part of the plot, and you have another plot that has the same data, but displayed in a different way, and you can see how you segment that data or select that data. So it enables you to rapidly develop your data analysis methods. So take a look at these things if you haven't seen them before, and try and find a way to use them in terms of your exploratory data analysis. The simplest way, use Matplotlib. You don't need to do anything fancy. See what kind of distributions you have, see what kind of extremes you have, and then from there, if you want to share it with others, use it in NPLD3, Plotly, Bokeh, and so forth. So moving on beyond that, let's say that once you have discovered or you've explored the data and you've discovered what you're looking for in the data, but you want to verify some of the results, you're going to basically look at the way that you can store the data in the environment. So that's data structures. And data structures is what allows us to store that data. And like I said before, lists, tuples, and dictionaries just won't do the job. And the reason is that it doesn't really allow us to basically traverse through that data in a way that's optimized for numerical analysis. NumPy does, unfortunately. It does, fortunately, allow us to do that very well. But it allows us to do that very, very well. Oh yeah, and also before I move on, I think we have some books from O'Reilly that are here from my book. How many books did you bring?
None.
Oh, none. Okay.
There was a mix-up. They didn't get them shipped to me, so after your presentation, all Q&A, we'll do a virtual giveaway. We'll like collect business cards or something.
Okay. Fair enough.
Well,
just in case, I came prepared. There's two more. So for people who have the first 4 good questions, I would like to have it as informal. So if anyone has maybe some like leading questions and they can't handle it, I'll let you know.
No, I mean, what's the criteria?
Yeah, anything that's just truly honest, like a really good inquisitive question. So if something's not clear, then please ask and I'd be happy to answer. Yes?
So just going back to the graphics package, what's the best graphics package for very large structures, say, 1 billion points or 100 million points?
So you probably want to deal with a package that doesn't render the data in terms of vector form, because if you have anything that's like a vector type plot, those data points is going to use a lot of memory. You probably want to use, as far as I can tell, at least the ones that I mentioned, the map of it, but make sure that you reduce that data in size before you actually pass an example of it. If you're going to do anything with something that's sitting as a vector within the browser, so something that's JavaScript based or SVP based, it's going to be bending your computer pretty bad in terms of memory. There are some developments that you may want to keep an eye out for, look for. I don't know the names of the packages because technology called WebGL, and that can be handled very nicely or connects very nicely with JavaScript. And there has been some effort in that environment where people are trying to use JavaScript to render larger data sets. And that's just because it's using the GPU and it's rendered into a non-vector form. Okay. That's a good question. So I have a book for you. So bear in mind, good questions. So I'm just going to give a little bit of an example of what NumPy is in terms of numerical arrays, and then we'll move on to things that are a little bit more complicated. And we'll also see some of the advantages in NumPy. So NumPy doesn't necessarily execute the operations of numerical analysis in Python space alone. It actually moves into C, and it's optimized in C. So when it's passed to C and it's moved back into the Python space, it can operate much, much faster than what you would typically do in, let's say, looping through a list or a dictionary. So I'm going to make the text a little bit bigger. It's, I think, maybe a little bit difficult for people in the back. Is that big enough for everyone? Okay.
Continuum is working on a library called Play, which is an extension of.
I'm going to talk about place. Excellent point. Because you did a foresight, I'll give you a second book. Okay. So basically, ignore the import comment. I just want to show you some of the speedups that we get. Basically, you have this line up here, which is importing NumPy as NP. So anything that you see as NP throughout is basically referring to NumPy. First thing we want to do is build basically a numerical array or NumPy array that's going to have 10 to the 6 elements. As you know, a list with 10 to the 6 elements would actually be a little bit heavy in terms of memory, as long as each one of those elements are unique from one another. And we're going to basically convert that list. Oh yeah, and also np.arange is similar to range. So when you do range and you create a list with values going from 0 or 1 to nth value, this is a similar representation of that. And then you have the way that you can convert that list back into, you can convert that numerical array back into a list. And that's what you're seeing here. So I just want to make sure that you clearly see both of those. So the magic of NumPy is that if you wanted to, let's say, operate on the elements within that array, let's say the array plus 5. So every element within the numerical array is now going to be boosted up by a value of 5. The numerical arrays have a feature called broadcasting. And it takes that information, puts it back into C, and then puts it back into Python, where that value has been broadcast to every element within the array. Whereas with a list, you can't do that. You don't have this broadcasting feature. And what you have to do essentially do that is basically iterate through that list 10 to the 6 times, adding 5 to that element. And we all know that Python is not very well specialized for doing those types of operations. So that's what you get here for trying to basically create a function that's going to allow us, in this case, not plus 5, but do a scalar to every element within the list. And if you were to take those operations, and let's say that we wanted to do the array, where we have, this is the numerical array representation, the array times 1.1, the 1.1 will be broadcast to every element on that numerical array, and then time it, versus actually going through this list here, this function which will iterate through that list, the speed up is quite significant. So the time it took for the numerical array was quite small, 10 to the minus 3, whereas for the list it was a factor of basically, 10 to 2 more than that. So this already shows just a very simple example that not only it's enabling you to broadcast values onto an array easily, but the speed up is also significant. So this is not only going to be something that you're going to see in numerical arrays, it's also done in SciPy. I won't go over SciPy that much in this session because we're going to cover pandas a bit more. That's something that's more broadly used right now for numerical analysis. But there are treatments in SciPy that would make this even faster. So if anyone's dealt with sparse matrices, that's a real common problem where you have a lot of values that are zeros and very little values that actually represent anything. And trying to deal with sparse matrices in a vanilla numerical array will not be very precise, will not be very quick, because you can have like 10 to the 8 elements, 10 to the 9 elements, or even 10 to the 10. Whereas with sparse matrices, you can go through that, I say, probably by a factor of 2,000, at least faster than what you'd ever see in a numerical array. So if you're interested in that kind of thing, make sure you look at the sparse section of SciPy. So when NumPy first came out, I think it was a real boost to Python, and it added some real value to Python in terms of numerical analysis. But now we're moving into a space where we're dealing not only with, let's say, things that are purely numerical, but maybe we also have things that are in some form of tabular data. So if you're not familiar with what I mean by that, easiest way to look at it would be an Excel spreadsheet. So in an Excel spreadsheet, you have basically this tabular data form where you have maybe indices, you have column names, and then you have some type of data in each column. And imagine that each one of those columns has a fixed type. So it could be that one column only handles strings, another type would only handle integers, another type would only handle floats, or double precision, single precision. So with that in hindsight, the NumPy community created something called record arrays. Don't try to remember this. This is something I'm only going to show you that is quite painful to try and do tabular data form with record arrays in NumPy, and I'll show you why pandas is that much better. So here's a record array. The representation in terms of what we're going to do is we're just going to create a record array from some fake data. And I'm calling this thing here, which is basically creating a matrix of 2 rows, and it's just filled with zeros. And the types would be integer, floats, and so forth. And what you have at the bottom, which we're going to add to it, is for the first column, so this is row number 1 here, is 1, a float, 2 dot, so 2.0, and hello. And then again, the same thing here, but now it's going to be 2, 3, or 3.0, and world. And then we can add that to the record array. Syntax is not, as you can see, is not quite informative or, let's say, intuitive in the way that you can generate this. So now the record array, there's another way that you can do it. We're going to do it again, same process as before. But this is the first pass of how we do it. This is the second pass. Also, for those who have my book or don't have it, if If you want to find out more details about this, you can actually find it in the book. So all the code, for example, is on GitHub. So if you want to go to GitHub, look at my name, you'll find the package, all of the code there, and also the explanations within the book itself. So here we have an np.a range. We're doing +1, and np.a range again. So again, this is the range, and we're going to have a float of 32 from 0, 1, and 2. And then you have hello world. Then to make it a little more complicated, now we're getting ready to add it. You have to zip it. And then last but not least, you can now feed it to the record array. So what this now has given us is a way to basically essentially have a tabular data set. And let's say that we have the names for the record array. So for each column, we call integers, floats, and strings. Then we can actually access that information in terms of integers. So as you see here, it says print record array integers. Yes?
You've got any bounce checking so that the wrong type of data gets put in wrong? You put any bounce checking rules associated with the columns so that you try to put a string in the number column. Okay.
You have to say it one more time, sorry.
Can you embed bounce checking or type checking into the column?
You can do asserts. You can do assertions, like you can create your own function where you actually have assertions in there to make sure that the value is the right type. Otherwise, it's basically just going to throw an error. And then other times, it will be silent, and you'll throw something in there, and it will convert it without you knowing. So you have to be very careful about that. It's not really consistent. So, good question. That's book number 3. Any other questions before I move on? Yes?
All this with Python 3.
Mm-hmm.
What's the status of that? And I guess, is it just as feature filled as 2, or is it still in progress?
It's still in progress. If anyone wants to correct me, I don't quite know because I only use Python 2, especially because a lot of the packages I use are still in Python 2. NumPy and SciPy should support Python 3, if I remember correctly. And I think also pandas. But I'm not 100% sure on that. And that's because I don't use Python 3. So the question you had was, are some of the packages that we're looking at, we're talking about today, are they supported by Python 3? My answer was, again, that I'm not quite sure, but I'm pretty sure that both NumPy and SciPy support it, and pandas I'm almost positive it also is supported. But there's a lot of work on trying to do that. So, good question. 4 books. We got more books coming in, so remember to chat with the administrators about it later on. So now you know that record arrays are incredibly painful to work with. This is something that I was actually working with well before pandas came out to store tabular data. And honestly, I didn't enjoy it at all. So I was very, very happy when I saw pandas come out. So pandas, in summary, and this is the part that I really want you to focus on, is an easy to use data structures and data analysis tool for the Python programming language. So this is a package, again, that's been developed by Russ McKinney and the open source community, and it's made extremely rapid development in the last few years, and it also has explosive growth in terms of use. Nearly every data scientist in Silicon Valley knows pandas. It's basically a common name. It's pretty much like breathing air. So I'm going to give you an example of what a data frame is. So before I move on, I have another question. Who has used R in this room? Great. So many of you are probably familiar with data frames in R, right? Okay. So this is supposed to represent something that's fairly similar or almost identical to data frames in R. So it's another way of working with data in a tabular form. So the first thing I'm going to do here is basically read a world cities population text file that's several million rows long. And it has these columns here. So you can basically say df tail and then close it with parentheses, and that will give you the first 5 rows within that data frame. And it shows me a few things. One, there's this column on the left-hand side, which is the indices. So there's some subtle, I'd say, importance about indices in pandas, which I'll explain a little later on. It's not necessarily the same in the way that you think about indexing in Python or SciPy, if you're familiar with that. And then you have the countries, the city, accent, city, so some of these will have some type of non-UTF-8 type encoding, region, population. Many of these cities will have no population, they're just far too small, latitude and longitude. So latitude, for example, will be ranging from -90 to 90, and longitude, depending on the way that the map is represented, will go from 0 to 360, or from 0 to 180 and -180. Another way that you can look at the data, so like I said before, in terms of the quote from the website, was that it's not just merely a way of handling data in a structured form. There's also a way of being able to do really quick and easy analysis with it. Yes?
So quick question, earlier you said the DF dot tail now it's ahead. Should that be the last 5 and here would be the first 5?
Sorry?
Similar to the Unix command?
Say it again? Sorry.
The dot tail.
Oh, the dot T?
Yeah, no,
Oh.
if you go back up, that should be the last 5, not the first. You said
Oh yes,
the first
tail,
5.
that's right, tail, that's a very good point. You definitely deserve a book. Yeah. Basically, tail is similar to head. So for those that are familiar with data frames, head is when you look at the first 5 columns, tail is when you look at the last 5 columns. You're not only merely limited to the first 5 columns, for example, so if we go to head here, you can also, ooh, I will fix that. Okay, it's reading in the data set. While that's loading, you can also say that I want to see, let's say, the top 10 values or the top 20 and so forth. Usually within the IPython notebook environment, if you do more than 50 of the heads, it'll just get truncated. It just won't show you anything beyond that in terms of the head function. So, for example, we have here 10, and we want to see the first 10 values, and you see that, for example. And if you do that with tail, it'll take it from the last value and 10 upwards, for example.
Question.
Yes?
So in the population column, you're basically using not a number to indicate that you don't know the answer or something? Is that what you're doing?
There is no information on the population there.
Okay.
Yeah, that's a very good question, and I'm actually going to go into how we can filter that out. So let's imagine now that we were trying to do some data analysis on this, and we wanted to see, let's say, the mean population, and we didn't know that the NaN was in there. Maybe we, unless we treat it in the right way, it could skew up the information that we have. So there should be some way that we get rid of it before we actually proceed with the analysis. So
But if you get rid of it, then you have to replace it with something else.
if you get rid of it, what?
If you get rid of it, you have to replace it with something else, or else there just isn't a population entry.
Well, yes, you'd probably be skewed to places that would only have population information, but that's better to know than to not know that, right? So as long as you know that and you mention that as a caveat in your analysis, then people understand how you derive that information. They can basically regenerate the analysis that you did. So there's another really nice function that this is the one that I think is the most important of tools of trade with pandas. It's just called describe. And what it very nicely does is it provides you the count, the mean, standard deviation, the min, the quantiles, and the max values. And this is just at first glance what's happening in those columns. So the columns I've transposed it so it's a little bit easier to read. So if I did it without transpose, the columns would be going downwards. So while that's processing, there we go. So you got population, latitude, longitude. And I'll leave it this way since it's a little bit easier to read on the screen. And it basically shows us the information that we're looking at. So like there's this mean population of 47,000 or 48,000. Standard deviations quite significant, so we know that the mean is not fully representative of what's happening here. And the other information that goes with it. So this is just a great way to get a quick analysis of the data that we have. Fortunately, pandas handles not a number values very nicely. It just ignores them. If you were to try and do this where you have a numerical array, a NumPy array, that has NaNs within it, unless you use certain packages that will specifically know that there's NaNs within it, it will just return NaN. So not a number. This is something that just the way that numerical arrays work, whereas pandas will just ignore them by default. Now let's say that we want to do a little bit more analysis, but we want to get rid of the columns that have strings in them, right? So we just only want to focus on the things that have the numerical values. Then we can do a very nice ability where we can just do drop on the columns. So axis 1 just means that we're dropping column-wise. Axis 0 means that we're dropping things row-wise. The indices also can be different types of numbers. So it doesn't necessarily have to be something from 0 to whatever. It can be anything that you want to feed it. So for example, maybe you have client IDs representing customers for your company, and you want to put the indices, indices to represent those client IDs and fill them in as well. This is very useful for features called merge and pandas, and this is actually almost equivalent to what the join function would be within SQL. So if you wanted to merge things based on two unique columns and two different data sets, and merge them together so that one row would represent one type of client, for example, with all the attendant information you would use merge. And so what you have here is you're dropping it, and again we look at it and we can see that now the table has been truncated in terms of columns, and maybe we also want to get rid of the NA values. See the populations here is getting rather annoying, and we'd like to just have some way to get rid of that for now. So we just do drop NA, and then that would allow us to just go straight through without having to worry about it anymore. So this is just a way of looking at the data and just kind of filtering it. Yes.
Dropping every row that has at least one and negative? Is that what you're doing?
Yes, that's right. That's a good question.
What was it?
Yeah.
Can you repeat the question? Restate.
Yeah, there's a lot of good questions. Sorry, say it again?
Can you repeat the question? He asked.
Would you restate the question?
Oh, the question, sorry. The question that he asked was that when you do drop in A, is it dropping a row that has an NA value in any column? And it is. So that's something that's a subtle thing to listen to, or to be aware of. So I'm going to talk a little bit about Blaze. Who asked that? Yes, that's a good thing. I'm not going to go into too much detail because it's still in a very, very early state, but this is kind of the next generation of what NumPy has added to Python, but in a much more scalable and also probably a little bit, I'd say, more Pythonic way of treating data. Pandas does a phenomenal job of doing it, but Blaze also does some new features that I won't go into too much about now, and that's just because it's a little bit beyond the scope of what I'm going to talk about. But Blaze is very, very exciting. The development on it, again, is very rapid, coming from Continuum Analytics, the one that we've also developed Boca, also the Anaconda Python distribution. All these things, everything that comes out of Continuum Analytics seems to be good. I don't work there, but I just like everything that they do. And Blaze is one of the things that you definitely want to keep an eye out for. I would definitely recommend reading up about it. The IPython notebook here will be shared online, so you can actually grab this notebook and you can just click on the hyperlink that'll take you there, so you can read up on it. So stats and probability. There's some fairly simple and rudimentary packages in NumPy that allows you to do some correlation analysis, has certain types of distributions, like a normal distribution, Gaussian distribution, and uniform distribution, or even a capability of shuffling indices. This is all in my book, and I wish I could talk here for days on end about what's in there, but I can't. So I'm just trying to just give you a highlight of some of those capabilities. So random sampling and correlation. Imagine that we were to try and find correlation between temperature and rain around the globe of the Earth. I don't know the answer to that, and this is definitely not going to be good data in the sense that it's just fake data and it's just randomly generated data. I just want to show what you can do with random generation with basically the random function, and also what you can do in terms of trying to do something just simply with correlation. If you're a stats buff and you're not familiar with Python and you're looking for tools to use, there's a very good package called stats models. This is a phenomenal package for doing statistical analysis within Python. So that's well beyond the scope of today's presentation, but that's something else that you want to look at. So this is temperature and rain. Function basically just provides latitude, min temp, max temp, and points. And basically, in this case, I have latitude is the absolute value of it, and I'm going to do a normal distribution, scaling with a value of 5, and the size of it will be based on the latitude here. So that's basically making sure that I have the same number of elements that will be temperature to the number of elements that's been passed as latitude. That's all I want to see. And then I get this temperature value. So I'm just, again, making sure that there's no negative values in here. To be or not. So in here, I'm doing a random integer. a random integer function, and basically its low value will be 0 and high value will be 2. And basically I'm looping through this, and long story short, I've already shown a little bit what I wanted to show in terms of the random tool, so this is the most important one, random. But long story short, what I do want to show is that imagine that you get the output from it, and you want to see if there's some type of correlation between the temperature and the rain. You just basically just do result equals correlation coefficient, and you get a covariance matrix that would represent what you're having here. And in this case, the results basically show that there's no real important correlation. This is going to be something that I think is a little bit more exciting, which is basically polynomials and differentiation. So we know that when we are when we differentiate the cosine function, we get a sine function. But let's imagine that we could do it from data itself. Imagine that we didn't even know that it was a cosine function, that we just couldn't recognize the cosine function itself. We had some very clean data points, and we wanted to try and find some way of differentiating those data points. So we have the x value, which is basically going to be a linear space representation from 0 to 8 times pi, so np.pi, and it's going to be 50 elements within that array. So that's going to be 50 steps from 0 to 8 times pi. And we have a y value, which will be cosine, and another y value, which is y2, which will be the sine of that. And if you notice, what I'm doing here is I just wanted to see that value of y2 when you subtract np.pi. And that'll become very clear why I'm doing that towards the end of this example. We're going to have a plot that demonstrates why this is important. We fit the data. So in NumPy, you have a package called polynomial, and we're going to import that. We're going to have that as p. And you get the coefficients, and you get the statistics about it. And so the first value again is that lens space value, so that's going again from 0 to 8 times pi, and then the y1 value, so that's cosine. So what we're doing here is generating data that's going to have a cosine representation of data points. Yes?
So what kind of precision do these packages have? Is it just integer or double integer or precision of the math?
64-bit. I think that's by default. You can declare it differently, but by default, if your architecture is 64-bit, it's going to go straight to that.
So the utilities won't try to change the precision.
Yeah, it's gonna stay with that precision. So if you multiply something that is 32-bit to 64-bit, if I remember correctly, it should always be 64-bit.
But let's say you had your own user-defined data structure with 48 bits.
You have, yeah. And there's the other thing that you have to be careful about. This is something that I was experiencing, let's say 6 years ago, which I wasn't aware of, that when you're multiplying these values that have higher precision, you're going to be inflating your memory usage. So you need to declare the type of that numerical array. So you can do something called AS type. Let me show you.
As a spin-off question, is it almost like Taylor's series where we're just going to basically say as long as within this delta, we'll stop? So at that particular point, it doesn't matter as long as we define that delta, we know the precision we want.
You can define the precision that it works.
Okay. So,
yeah.
So in that case, it doesn't matter. We would just basically say within this amount. For example, you know what I mean when I say?
Yes.
Okay.
Yeah. So I'm just going to create a new cell in here within the notebook. So I just wanted to clarify this. So x, if we looked at it right now, so I'm just going to, so we got the values. You get a whole bunch of small numbers, and it has, if I'm correct, 64-bit representation within memory space in Python. If you wanted to force that to be 32-bit, then you can do .as type and then float, or np.float 32-bit, and that will force it to be 32-bit instead. So that will save you space. And there's been many cases where I actually ran into this issue where I need to reserve that memory for something, so I can force it down to 32-bit.
So for the 64-bit, that's unsigned number, right? If you sign it, you go back to 32 for the signed number.
I don't know. That's a good question. I haven't tried that. So I really just work at it in a way that I can get my results. So
yeah. Because for signed, you need that.
Yeah. So right now it's 64-bit. Yes. Okay. Right, so going back up to this. So basically we get the results, and we're going to do a, basically differentiate the coefficients of that polynomial. So we have a function called polydir, which is just differentiating a polynomial. And basically I want to take that information and fit it, and then I get this new y-axis value. So this is going to be the representation of cosine if I'm differentiating sine, and that's going to be called dfit. Sorry, it's going to be sine. That's going to be representing the differential of differentiation of sine. So this is now you're going to be seeing a little bit of something that I didn't explain before. There's another package called Seaborn. Anyone use Seaborn before? Curious. Okay, so there's a really bright guy, Mike Raskin, at Stanford from, I believe, the psychology and cognitive neuroscience, who developed a package called Seaborn for statistical plotting. So it sits on top of Matplotlib, and it allows you to not only do nice statistical plots for analysis, but it also provides very good default settings for style. People who have tried to use Matplotlib with default settings can probably agree with me that they're not exactly beautiful in the way that the plots come out. They're very static. Basically, Seaborn allows you to make things look like ggplot. So ggplot's a very nice package with very good grammar of how to do good plots within R. So you'll see the results from that in a minute. So basically here what I'm saying is I just want the style for the plot to be ticked, and because I'm giving a talk today, the context is going to be talk. So that basically means that the font will be a little bit bigger, the lines will be a little bit thicker. This makes it much easier for people to see. So I'm going to be declaring the figure. I'm not going to state too much about it, but what I really want to show you is the results. So this is the green dots represent the data points, and the lines represent the actual data, so the cosine and sines. So this is not data that's been derived in any way. This is the real data of cosine of that linear space array X. So in the top one, you see the data, and the data basically, with the representation of fitting, which is the line, shows you where the data point of the line as a function of X. And when you differentiate it, you get the differentiation. So sine to cosine or cosine to sine. So it's nice that you can do this with a very simple package like NumPy. You can also do much more features within SciPy itself. By the way, how much time do I have? I'm wondering if I need to speed up.
No, you got plenty of time.
I got plenty of time?
Yeah.
Okay. So this is, I think, maybe something that would be a little bit more interesting for a lot of people, which is optimization. Basically, you already do forms of optimization with many types of data where you try to, say, fit a linear function with data points. So an example would be this one that you see here. So I'll explain this, and then we'll go over the code itself. You have the function, which is basically plotted in the black line. And so this is the actual function, the line itself. There's no noise added to it whatsoever. And then the orange dots is representing data. So I actually add noise to the function itself, the functional form of that data representation. And then there's the best fit. So basically doing a linear fit to that with SciPy in terms of optimization. So here we have the code was extremely simple, and I think this is such a nice way of being able to optimize your results. So here you have a function, x, a, and b. So basically it's a of x, the scalar times x and b, and x is the value that you're ranging over. Now we're going to generate some clean data, going from 0 to 10 in 100 steps in terms of the linear space, and then we're going to apply that function, so we get the output from that, which is we're going to have here a being 1 and b being 2. So a again is the scalar and b is going to be the offset. And then we're going to add some noise to it, and that's where the noise comes from down here. So we're going to be adding noise to that data. And so you can imagine in the real world that data never comes, or let's say observations never come in a perfect form. There's always going to be some spread due to the instruments that you use, or just the way that the data comes in. If it comes in clean, I'd be highly suspicious. If it comes in with a little bit of noise, then I think that's okay, that's believable. but it would be great if you can find some way to represent in the functional form. So executing a package called curvedFit is a package that's available in SciPy. So that's this one here. So there's a sub-module called optimize from SciPy, and then we're importing curvedFit. CurvedFit, you apply the function, and then you apply the data in this case. And imagine that we don't have that clean data. So we have yn, which is basically y noise, and you're going to fit it. And you basically get the best fit value for the parameter. So this is A and B. So A value of 1.04 and B a value of 1.5. And if you look here, it's 1 and 2, it's not exactly great, but it's close enough for now, or 1.6. And so that result, when you visualize it, is here. So again, there's two things to learn from this. Doing this with SciPy in terms of optimization is incredibly easy. You just need to find a way to define the functional form that you're trying to fit. So in this case, it's a line, so that's the function. And you get results with it without very much work. It's probably one of the easiest examples I've seen that can actually allow you to optimize data. Yes?
Are there routines for linear algebra on sparse matrices in Python?
Yes, the sparse matrix routines is within SciPy.
Oh.
Yeah. So if the question was, are there routines or libraries to deal with sparse matrices in Python? And yes, there is, and that's within SciPy.
They have linear algebra.
Oh, linear algebra. I'm not sure. That's a good question. I haven't tried it that way. I haven't actually had to deal too much with sparse matrices in that sense. Good question, though. Okay. So nonlinear cases. So this is a great way of understanding things that are happening in a linear space. But what about if you have a nonlinear example? So the code is almost identical to the previous example, but I just wanted to show this as a typical case that you'd have in astrophysics. In astrophysics, you may have what we call basically a light profile of basically how light is absorbed or emitted from an object. You can imagine a black body radiation type object, and let's say that you throw some gas around it, and that gas has a very specific frequency that absorbs the energy from, or the light from the black body object. So you're having two things. One, you have an emission from that black body object, and then you have absorption. And we constantly deal with this in astrophysics all the time. This is basically the blueprint of a star. This is how we identify stars without really knowing too much about their sizes, because we can't really see them, they're too far away. Yes?
Are you going to do anything about discussing statistical significance of that peakable enough? If I didn't know I had generated it, I wouldn't.
Yes, so you can actually get values of the covariance matrix from it, and you know the statistical significance of that.
That's in SciPy.
That's in SciPy, yes. Okay. Again with SciPy, so you will see that as well. Okay. Just like any other package, you'll always get the statistical significance of that fit. Okay. But it's also good to see it visually as well.
Sure.
Right? So here I made the data rather noisy to basically throw a curveball at the curvedFit algorithm. And as you can see, with the noise, it does impressively well in terms of the fit. So maybe it's not perfect, but it's fairly close. And I'll show you the code. It's, again, something that I think is just strikingly simple and almost beautiful. So you have the function, and basically this is just two distribution representing Gaussian distribution of a sort, and you have the values for the mean, the median, the means, and the sigma values. And you're passing that into the curvedFit algorithm. So here's the x value again, which is lens based from before in terms of the linear example. And then you have the function. So you have x, you pass that in with all the variables that you want to pass in. And then you add noise to it, which is here. And then the fitting is done here. CurvedFit, almost identical to the previous example. The function itself, the lens space value, so going from, ranging from, in this case, 0 to 20 in 2 steps. And then the noisy data set, because we can pretend that we don't know the real data set, and then throw in those variables. And then the output that we get from that is here. So it's basically telling us what those values are for the corresponding input parameters for the function. So if you look at that there, then the input parameters gives here. So those would be the best guess in terms of how to fit that. If you want to see the actual values, just print out p covariance. So that will give you the covariance matrix. Yes?
How well does curve fit scale to high-dimensional, like multi-dimensional data?
Say again, sorry?
Multi-dimensional data? So you have multiple
multi-dimensional.
predictors. How well does it work on that type of data? I mean, how does it actually fit data?
I can't remember the algorithm that's within it. It's a very simple algorithm.
You're not telling it what kind of model.
No, that's right. It's the simplest fitting algorithm. I should remember the name
It's
of it.
polynomial. It's a Taylor series, probably numerical method you use kind of knowing and it'll actually converge at some point and that's when you stop.
Could be, but I'm not. I can't remember, unfortunately. If there is a package, if you actually look within SciPy, look for another one that's not called curve-fit, and now I actually provide you the name. So, yes.
So that seems to work pretty good if the noise is Gaussian, but if it's not Gaussian, you might want to throw away the top, 10%, bottom percent.
Yes, that actually is going to throw it off. So if I remember correctly, this model will assume, or this optimization algorithm assumes that the distribution is close to Gaussian.
So, but if you wanted to do something like throw away the top 10%, bottom 10%, is that function able to do that, or is that something you have to?
I haven't tried. I think it should be possible. I just haven't tried that. Yeah. Also, there's more complicated fitting algorithms out there, especially let's say like MC-NC fitting. So these very simple types of fits will have severe issues with data points if they have like a big well in terms of the data points. There's one called MC, so just EMCEE. The paper I think is called MC Hammer. Yeah, it's a great paper. It's written by a good friend of mine, also an astrophysics, very bright guy, Dan Foreman-Mackey from New York University. It's very nice. It's basically space invariant, so it can deal with logarithmic distributions really well as well. That's very nice. Yes?
So is there any online documentation on all the packages and what's the algorithm underlying all the functions?
Say it again? I can't hear you.
Is there any online documentations describing
the algorithm?
Yeah.
Yes, there is. If you just go to SciPy and actually look at it, they'll have links to the packages that they use for it. So like where the code actually comes from.
Okay, so is the documentation up to date? Like
yes, the documentation is updated. It's always updated. It's very frequent. So the question that you had was, is the documentation for SciPy, if you want to know more about the fitting algorithm, updated, and is it available online? Yes.
Is there much in the way of document strings in the application?
Yes, there's also document strings. So you can basically look at the document strings and you find the information as well. That should actually be identical to what the documentation you find online. But in the HTML form, you'll have the hyperlinks to the different information resources. Yes?
So in this example, is P0 the initial value of those parameters?
P0, which part? Sorry.
Halfway down.
The curve fit.
Oh yes, that is the initial values. Yes. Thank you. If you wanted to see, let's say, like a slightly better fit, so let's say that we want to make that noise a little bit less noisy, and we can check it out. As you can see, the fit significantly better visually. You also get that from the covariance matrix as well. This is going to be, I'm going to speed up a little bit, but I do want to talk about interpolation as well. There are some cases where we don't know what type of function to fit to something. So if we have some type of data point and we don't know how to best fit it, but maybe we want to see if we were looking at representation of data and we want to see what how it would be shaped from point A to point B, but we have no way of actually providing a good equation to fit it, then you can use interpolation. And this one's going to be a little bit nicer, which is basically in terms of eye candy, which is going to be a two-dimensional fit in terms of interpolation. And the result basically here, the code I think I'm going to just have to pass because I do want to get to an example before we end, is basically showing this. So on the left-hand side is just kind of a ripple function, a wave function, that oscillates from the bottom left corner all the way up to the bottom right. And the middle one is showing you the sampled data points. So in this case, if I remember correctly, it's about 2,000 data points that's sampled out of this image. And then I want to reconstruct it. The image on the right-hand side is the reconstruction using a two-dimensional interpolation fit. You can't see it too well from your distance, but if you were to look at it on a laptop, you'd actually see it's a little bit coarse and that's just because the type of interpolation function I'm using in this case. You can actually make it smoother if you wanted to. There's several different types of interpolation packages within SciPy. This one's called a smooth bivariate spline. So for those who are familiar with interpolation functions, it's a very common one. And again, the plots look nearly identical. On the left-hand side is the real data, sample data points. The right-hand side is the representation of it. As you can see, it's pretty much as smooth as the original the original image. But the top right is a little bit messier, and that's just because of the nuances within the bivariate spline. So don't worry, the notebook will be provided for everyone to download after this, so you can look at it yourself in your free time. Now I'm just going to talk a little bit about machine learning, which is kind of my role at the moment as a data scientist. Machine learning is becoming more and more prevalent in the scientific community in terms of academia. Especially in astrophysics, it is definitely becoming more prevalent, but we do prefer to find or like to fit information or data or make predictions with, let's say, understandable equations. So traditional ways of understanding information that we can just solve with differentiation, integration, integrals, and so forth. And machine learning takes that out of our hands. So we've always been a little bit uncomfortable in using it because it is hard to understand what the machine is doing on the other side. Not in terms of, let's say, linear regression or logistic regression, but if you go into random forest and so forth, things do get much, much more complicated. But I just want to show, in terms of the world that I've been working with lately, this is using machine learning in everyday life. And this is actually not my car, but I had a car similar to this when I was living in Australia. And not the same painting, I didn't race it. It's just normal commuting. I wish I could race it like that, but it wasn't quite that way. And I wanted to sell it. But I'm not very familiar with the Australian culture. I'm not Australian, I'm actually from the US. And I wanted to find what would be the best price for me to sell that car. So I decided to use something called Kimono Labs. If anyone hasn't heard of that, they make a great API service they can use for free. You basically grab information from websites in a very structured form, and you can access the information in Python if you want as well. And what I did is I basically took that information, pulled it down, and actually I'll show it to you so you understand. Car sales. Here we go. So you have this, and you can say that you want some type of car. And what I want to do is pretend I'm a buyer, and I'm looking for a car. And I say, I'm going to look for that one.
Nice.
Yeah. And you basically get a list of prices. So this is a very structured website. And as soon as you start, as I think probably many of you have done this before, is you basically cycling the information off of this kind of website because it's structured. And you can use a nice package called KimonoLabs.com where you can actually just point and click to say what structures you're interested in, and it will reiterate on its own for you and get the information ready for you to pull down in your Python environment. So Kimono Labs is a great thing. So basically what I did was I was looking at this. Imagine I was selling that race car that you saw in the image, and then I just basically parsed the information about the title, the options of the car, and the price and the mileage, or in this case the kilometers. So I have a data set that was prepped by Kimono Data, and this is the data within it using pandas data frame. And as you can see, the columns are year, price, mileage, and seller type. And the reason why I did seller type is because I'm not a dealer. I'm a private seller. So I wanted to see if I maybe need to adjust that price if I'm a seller. A private seller instead of a dealer. And so in this case we have a Hyundai i30, a great car, I miss it. There's the prices, mileage, and the dealer, like I mentioned before. If you're familiar with scikit-learn, so there are a few extension packages that are built on top of SciPy. There's one called scikit-image, which is covered in my book, which is a great package if you're doing any type of image analysis. And then there's scikit-learn, which is kind of the nuts and bolts for simple machine learning. Well, not simple. It's a very extensive library, so you don't really have to worry too much about the details because they make it quite easy to use. And the one downside is that, well, it's not a downside, but it's just a feature in terms of machine learning, that your data can't really be strings. So if you have strings in there, you have to put it in some type of integer form to represent a class, for example. So that's what I did here. So there's just this little thing called intergize that just converts things that are not integer into integers. And like any type of real world problem, you have to do a little bit of data munching before you can actually do some analysis on it. And that's what this is done here. And then I basically going to do two things. One is I'm going to split my training data, or the data that, not training data, but the data that I want to fit as a design matrix. So the design matrix in this case, let me just open up one more cell here so you can see what it looks like now. So I'm going to read that in. We're going to see that representation of the data. And we're going to clean it up. And this is what the data looks like now. So now it's just limited to things that I'm going to work with in a very simple categorical format, which is year, mileage, and seller type. You'll notice that the price is no longer there, and that's because I pulled it out. That's going to be my label. That's the thing that I'm going to be using in terms of the linear regression for the labeling. So I call in the linear models from scikit-learn, and this is the linear regression. And I'm going to basically fit that data. And there's going to be a caveat that I'll mention now, but for those that are not familiar with it, I did do a little bit, I cheated a little bit in this one. I overfitted my data. And that's because I didn't really do a training and test data set here in terms of validating. But this is just a simple example of how you can do it. So you get the data frame with the design matrix in this case, and Y was the label. So the data frame for every row, in this case here that you see, is representing the information about that car. So the year, the mileage, and the seller type. So seller type 0 is a dealer, seller type 1 is a personal, basically a personal seller, someone that is not a dealer. And I'm going to say that I have a 2013 model, I have 13,000 kilometers, and I'm a private seller. And I want to see what would be the recommended price based on the linear regression. And it's going to be close to about 19,000. So I didn't actually put the column for that price. I put it a little bit higher, but I figured it'll work. The surprising thing is that if you actually put it in respect to the dealer, you can sell it for higher. So, but that's not too surprising in the sense that you know that they can do certain things to the car in terms of like checkups, certifications. They can take care of all types of things that would be complicated in terms of buying it from a personal seller. So they have a market price on that. And in this case, the results were good. Car's still on sale, but I'm sure it's going to work out eventually. And it basically gave me a means to take that data and to find, in a very smart way, a good price to set it at. And I think that's a great way of doing it. So in summary, basically I showed you some small things that you can do, or great things that you can do with SciPy and NumPy, and simple machine learning with scikit-learn. And these examples are just of a few within the book. So if you do want to check it out, please do. Also the examples, all the code examples, beyond this is provided on GitHub. So if you go to GitHub, you'll find it there. So let's see if it works. There we go. And all the code is there. So if you actually want to go through, you can play with it, do your own thing. So thanks a lot. You're welcome.
Okay, now's the open access part of our meeting where you get to...
More announcements?
Oh, are there more announcements?
How about Q&A for...
More Q&A. Oh, go ahead.
So I don't know if I know
We show projects. We show projects.
Sure. Oh, you want me to give a short talk yourself?
Sure.
Tonight?
This is a 2-minute lightning talk, correct?
Sorry. Okay.
In a minute.
Okay. Alright. So I was using this pandas and pandas. I don't think it would be a quick memory model.
Okay. So the question was if you've recently been using pandas and you found it to be a big memory hub. What kind of data are you using?
I was using the pandas that feed into the
Oh, yes. That's kind of in beta state. So this is the three-dimensional version, right? So that's not necessarily fully fleshed out. They're still working with that. I couldn't comment too much on that, other than that it's still being developed. So there could be some memory issues in that as well. Yes.
I ran into an issue where I learned the hard way that pandas share is dictionary when you copy items has to do with copy. So then if you start to just see weird things happen. Are there any other like pitfalls like that to be aware of that?
Indices. Indices is probably one of the biggest, I'd say, nuances in pandas that can be. So let me just repeat your question. He says that he's had some issues in terms of using pandas.
When you copy an item.
Oh yeah, when you copy an item. So sometimes when you copy an item, certain things will be passed from one pandas object to another, and that can be problematic. In a similar fashion, he asked for a tip if there's anything else that you should watch out for. And I say probably this is the biggest issue that everybody should be watching out for in terms of pandas. It caused me nightmares, which is that when you're trying to filter something, let's say like you have a Boolean array, and a numerical array, if you have a Boolean array, say let's say true, false, or like a where statement will return integer values of the rows that you're interested in. The result with an array is understandable and intuitive. If the rows that you have from 0 is always the top one, and let's say the last row is 100, when you index it and you're filtering it with those values of let's say like 1, 10, 50, 51, and 100, you're going to get those rows back. But in terms of pandas, that's not necessarily the case. It actually depends on what kind of function you have. There's something called .loc, so location, or .iloc, or .ix. They all behave slightly different, and they do indexing slightly different. And so you can imagine that if you're trying to filter it, you may be actually filtering on indices rather than order. And that can lead to a lot of problems. This is some that wouldn't necessarily break your package or your program that you're writing or your analysis, but it would give you results that you wouldn't understand because it's not necessarily breaking. So that's something that you want to pay attention to.
What's your experience with a garbage collector? I find that it doesn't clear memory fast enough.
What version of pandas are you using? The latest one? 1.15? Okay. I actually haven't really noticed any real issues. Even on my own laptop, if I'm doing something big, I'll usually pass my Python environment analysis to an EC2 instance on Amazon that has quite a lot of memory, so I don't really have to worry about it. But if there is an issue, you should probably check into it and see if you need to report it. Okay. So.
Yeah, I'm not happy with that.
Oh, okay. Well, the Blaze is maybe another alternative, but it's still an alpha state. I wouldn't adopt Blaze yet. But, yeah.
So when you have a lot of values and values in your data set instead of multiple use rows, is there any possible to create new values to replace these?
Yes, replace. It's just called data frame, df.replace. Also, in replace, you have the first input value, or the first input that you have in the function is, let's say.
Like how do you generate random values?
Oh, random value for each row. Wow, that's a little more complicated. Let's save that question for afterwards. And that's going to take a little more description. But that's a good question. Yeah. Okay. Any other questions before we move on? Okay.
You don't have questions after.
Okay, sure. Great. Thank you, everyone.
So just a couple more announcements. I know that other people probably have announcements too. We have someone who wants to do a lightning talk for an announcement as well, and I won't stay there for a second. I have two announcements as well. I'm one of the organizers that is on the meetup, and we have a couple more meetups next month. We actually talk about pandas in more detail, so please sign up for that one. Also, I'm doing an Ansible tutorial online for free. There's only slots for 10. It's free. If you don't know what Ansible is, or if you ever want to learn how to make your own Ansible playbooks, please go see that talk online on the meetup site. And there are probably other announcements for people too. Probably people looking for jobs and people looking to hire as well.
Someone over here had something he wanted to. I saw a hand over here.
It's a 2-minute lightning talk.
Okay.
I'm going to go ahead and stop the broadcast since we're going to change now.
just wanted to share a project I was working on. So basically, I was trying to figure out what's a good way to make the scripts that we're creating, or some of the things that we saw up there, as accessible to people as possible. So what I did was created this thing where for Python scripts, R scripts, and Ruby scripts, you could just throw in your script and point and click to instantly create an API on top of your string. So I just want to show people how that looks, and then just grab some feedback for if anyone wants to try it out after. So here's how it works. Whoops. So I'm just printing something, and then you double click, and then it immediately gives you a form to actually run the script, and you can put in any arbitrary code. And it says, hey, my name is Paul. And so the reason that this kind of makes things accessible is if you could do this with a bunch of your scripts, you could actually send, instead of raw functions, just forms to non-engineers that might just fill in inputs and actually be able to run your script. So here's like a basic one where the source.
Increase your font size?
Oh, sure. Sorry about that. So the source code here is importing like a faker library, and it's making a bunch of fake data. But really, the only thing that someone needs to see is how many rows do I want. Then you click on that, and then you get a data set that you could download. So that I thought was pretty cool. But I was wondering, we were talking about visualization. One of the big problems, I do a lot of D3, and I'd love to run an R script or a Python script straight from my D3 code. And it's kind of like the opposite of what we were talking about, where can we generate D3 from Python? That's one way of doing it, but sometimes I think that's a little limiting because it's hard to think of what's everything that I might want to generate for D3. So if you start backwards, it's a little easier. So what I did was, what if we could just take all these scripts and just create an API? So maybe from your front end, you could call Python scripts, or R scripts, or Ruby scripts, or from Python, you can call Ruby scripts, whatever you want. So here's an example of how it looks. Here's just like a basic string graph. And I was thinking maybe, we could make a little clustering algorithm straight from pandas. And I just wrote this up while we were talking about pandas. So how it works is you just go into Python, paste in your script, and you're gonna want to throw in JSON, so you double click that, and make that text. You're gonna want to know how many clusters you want, so you double click that, make that number, and then when you're done, you just publish, and it gives you an API key. And then all I was going to show is that if you take this API key, and you could highlight this whole thing and then put it back in your script for your visualization, you can actually, and go really fast, but you could actually just run and call workers in any language straight from your front end. So let's see if this actually works. There it is. So it just took that string graph and just did a k-means clustering in Python and returned the JSON. So you could just run any language you want straight from your front end. So that's what I'm working on. Would love people's feedback if this is something they think is useful, or any questions.
Really quick question.
Sure.
Do you have a tutorial on the website?
I'm putting out some documentation. So the basic documentation is what are the inputs that we provide, and how does that pop up in your actual code. But if there's anything confusing, I'd love to add to that.
So you might want to say what your website is.
Oh, sorry, it's forms.blockspring.com. So that's all. Thank you.
Hey everybody, it's Wesley Chan, author of Core Python. Just wanted to send the last reminder that I have a 3-day intermediate class coming up. I mean, it's okay for intro people too, but I don't think you guys are intro Python people. But it's the 30th, 31st, and the 1st, and it's near SFO, so lots of parking across the street from the BART station, all that stuff. So come chat with me. I think I got a coupon code on me as well too. Regular price is $14.95. It's 3 days, includes lecture, labs, lots of code labs, and copy of the textbook. All right, so I will talk to you guys afterwards.
Which textbook? I'm just curious.
Core Python.
Core Python.
So I have one more announcement. Basically, the company I'm working at is called Stitch Fix. If you're not aware of it, check it out. It's called stitchfix.com. We have a very rapidly growing data science team along with data engineering. So we have some very good talent that we've been pulled in recently, such as Jeff Magnuson from Netflix. And we need people who have expertise in data engineering, and we also need people who have expertise in data science. If you're interested, feel free to reach out to me, and I'd be happy to chat with you some more. Thanks.
So O'Reilly's given us 10 more of Eli's book to give away, and unfortunately they didn't make it in time for the meeting, so I think I'm just going to collect business cards for anybody who's interested. So if you're interested, give me a business card, and if anybody has a plastic bag or a box or something I can put the cards in, I'd appreciate it. Makes it a lot easier to draw from.